Hello, this is Mrs. Scarple, and in this video I'm going to go over continuous growth and decay exponential equations. On this slide you'll see that I have two equations, one where the exponent is positive and one where the exponent is negative. When the exponent is positive, this is the formula that we're using for continuous growth. When the exponent is negative, this is the equation we will use for decay. And as we have seen in other lessons, P is going to be our starting amount. A is the amount we end with. R is the rate of growth or decay. Keep in mind that you need to convert the percent to a decimal. And T is the number of units of time. When we were doing the compound interest, time was always in years, but when it comes to just exponential growth or exponential decay, time could be as small as every second, or it could be as large as, let's say, every 1,000 years. So just pay attention to what the problem is saying and make sure that you label any time with the appropriate units, especially if that's what we're solving for. So let's take a look at our first example. The growth of the virus through a population is continuous until it is somehow contained at a rate of 3% per day. So that tells me that R is going to be 3% or 0.03. Remember, when you are converting a percent to a decimal, you either move that decimal 2 units to the left or divide that value by 100 to get the decimal. The current outbreak has confirmed 5 victims, so we know that P is going to be 5. How many people will be infected with the virus on day 30? Since our rate is per day, that means our T value in this case is going to be 30 since we're talking days. So we have a P value, an R value, and a T value. We can now use the formula, especially since this is growth. We can use that first equation that we saw on the previous slide. A equals P times E to the power of RT. Remember, E is that value that's approximately 2.71828. It's a value that we'll use on the calculator. When we do these, we just go ahead and enter it into the calculator. So for this particular problem, to find A, we're going to take 5 times E to the 0.03 times 30. So let's get our calculator here. And we will type 5, and then we will open the, we don't need to open parentheses, excuse me. We want that value of E, which if you look above the natural log button, you'll see an e to the x that's in blue, so we have to press second natural log, that's the ln button, and it automatically gives us the exponent we need to enter. So we have 0.03 times 30. And then we press enter and we see that it is approximately 12 people. So A is approximately 12 people on day 30. Now, we can use this formula to find rate, or we can use it to find time. So this next part of it, when does your model predict there will be 50 victims? In this case, T is our question mark. A is going to be 50. And we will use the same p-value and r-value as we did on number 1. So I will set this up as 50 equals 5 times e to the 0.03 t. Well, the first thing we want to do is isolate the power of e. To do that, I need to undo the 5 times e, and to do that we divide by 5. So now we have 10 equals e to the power of 0.03 t. Now this is an exponential equation because our variable we're solving for is in the numerator. This is an exponential equation that we are solving. Remember that logarithms undo exponents. Because this is a base e, we want to use the logarithm for base e, and that is the natural log, ln. So I'm going to take the natural log of both sides. I'm not going to find the value of natural log of 10 just yet. We will use the calculator to do that, but we're going to wait until the last moment possible to calculate that value. So when I take the natural log of e to the 0.03 t, we're left with the exponent. Now I need to isolate the t. 0.03 is being multiplied with t, so that means we need to divide both sides, because what you do to one side, you must do to the other side of an equation. That's how we keep them balanced. And now I can actually take the time to enter into my calculator natural log of 10 divided by 0.03. So let's get that calculator back. I'm going to clear what I have, and we're going to use that ln button. It's right next to the 4. So natural log 10, notice it had opened parentheses before the 10. We need to close the parentheses after the 10, divided by 0.03. And this tells me it will take approximately 77 days for there to be 50 victims. So approximately 77 days for T. Let's take a look at another example here. Here we are talking about a radioactive material that decays. That means we're going to change the formula we work with to A equals P times E to the negative RT. It's a decay, so that exponent needs to be negative. Continuously with a half-life of 3 years. The half-life tells us that after 3 years, only half of the amount of goo we started with is remaining. If we start with 10 pounds, that's going to be our p-value of radioactive material. How much will be remaining after 5 years? Well, I have a principal amount. I have a time, but I don't have a rate. And this is where we're going to use that half-life information. We're going to use the half-life information to help us find our rate. So half-life is when only half of the amount remains. To find our rate, we're going to have to use 5 as the value of what's remaining because we want half of what we started with. So 5 is going to equal 10 times e to the negative r times, and the time period of that half-life is 3 years. So negative r times 3. Just as I did in the previous problem, I want to divide both sides by 10 so that I can get the power of e isolated. And when we do this, 5 divided by 10 should give us 0.5, that we only have half of it left. And I'm going to write it as e to the negative 3r. So it's written more as we're used to, or more like we're used to seeing algebra written. Again, this is a base e power, so we need to use the natural log to undo that base e power. So we take the natural log of both sides. Again, I'm not going to find the natural log of 0.5 until I know what that final step is going to be. So natural log of 0.5 equals, we're left with the exponent negative 3 times r. Divide both sides by negative 3. And now we're ready to enter into the calculator. So we have the natural log of 0.5 divided by negative 3. Oops, I didn't close my parentheses. Let me go back and fix this. So the 0.5, I need to close the parentheses, then I can divide by negative 3. And my answer is a rate of 0.23. So a rate of 0.23 we need to convert that to a percent. So that's going to be approximately 23% is the rate of decay. How long will it take for the amount of radioactive material to decay to an amount less than 0.5 pounds? Well, we're going to use that rate, and I just remembered I didn't finish the previous problem. So let's go back. Let's pause. Sorry about that. We haven't found the amount remaining after 5 years, so we're going to use this rate, we're going to use the 10, and 5 is going to be our t value to finish this problem. So we're going to have how much will be remaining? We're looking for the A equals, we know P is 10 times E to the negative 0.23, and T is 5, so negative 0.23 times 5. And then this we can enter in the calculator just as it is written. Times E, so that's the second natural log button, negative 0.23 times 5. And we get approximately 3.17 pounds. Of radioactive material left after 5 years, if we start with 10. Now, to go to that last problem, we're going to be looking for how long it takes to get less than 0.5. So the R value that we found with the previous problem of 0.23, oops, let's write that again, 23. We had a P value of 10. We don't know what time is. We're being asked how long, so time is our question mark. And A is going to be 0.5. So if I use my formula, my decay formula, I'm going to have 0.5 equals 10 times e to the negative 0.23. Write that a little bit better. Negative 0.23 t. We want to isolate the power of e, so divide both sides by 10. 0.5 divided by 10 is going to be 0.05 equals e to the negative 0.23 t. We can now take the natural log of both sides. Natural log is what we use to undo a power of e. So we're going to have natural log of 0.5 equals negative 0.23 t. And then to solve for t, we divide by negative 0.23. So grab that calculator again. Natural log of 0.5, close those parentheses, and then divide by negative 0.23, and we have approximately, oops, it shouldn't be 0.5, it should be 0.05. I didn't transfer my numbers correctly, so let me rewrite my problem. This should be 0.05, not 0.5. That number seemed a little high to me, or a little low, excuse me. So now let's try that calculator again using the correct value. Natural log of 0.05, close the parentheses, divide by negative 0.23, and you'll see we get a much different number. We get about 13 years. So t is about 13 years for us to get exactly 0.5. So it would need to be more than 13 years to have less than 0.5 remaining. And this concludes our video on using our compound continuous formulas for growth and decay of exponential equations.